Okay, chat, hello. We're going to move into part 3 of today's discussion, and that is we want to talk about T-invariant subspaces. So we've done all of this work to think about change of basis. We've done all of this work to develop this kind of nice commutative structure between general linear transformations of vector spaces. So now I want to put it all together. And the leading question here is going to be, okay, so now that we have this new matrix structure, and we know that the kernel is somehow related to the nullity of the transformation matrix that represents T, how do I, how can I use that information to the best of my ability, right? Like, how can I do a little bit more work here with that? So it's going to take a little bit of construction to kind of get the job done. But we're going to start by kind of looking at that general linear transformation and setting it up in a square kind of way, and see where it goes. So we're just going to start right off the hop, and we're going to define a linear transformation as a linear operator. So we call a linear transformation T from vector space V to itself a linear operator. And so a couple things pop into mind if I'm thinking about a vector space getting mapped into itself. I might be curious about how I can represent, like, if I have this kind of rule that describes T, how does it change if I choose different ordered bases, right? So that's one thing that we might want to think about. So how does the matrix that represents our linear operator change as we change ordered bases? So I think that's an interesting question to ask, right? So for two different ordered bases, what's the relationship between those two matrices that represent T? And then the other thing that is kind of interesting is, like, are there any invariant subspaces? So, and this kind of choose your own adventure can go on in a couple of different ways. So we could think a bit more about the kernel, and we could start thinking about stuff that gets mapped to the zero vector, right? So, like, in some sense, like, what's the dimensionality that I lose as I move my way through T? Or what dimensionality do I save, right, or preserve as I move through T? I'm going to ask a bit more of a harder question, which is, are there subspaces of V that as I move through T, like, really don't do much? They kind of just get mapped to themselves effectively. So we can hopefully answer both of these questions within the next hour or so, and then we're going to call it probably quits for the day, unless there's some stuff in Discord that people want me to clean up. So what we're going to do is we're going to draw one of Anders' favorite maps. So here's what we have. We have vector space V and vector space V, and we have some kind of linear operator that's mapping V to itself. Sensation. I don't even know if that's going to be allowed, to be honest. I don't think that's going to be allowed. Yeah, exactly, Anders. Yeah. So Suno did not want to give you a Spanish opera with those specific lyrics.
Zeta maps are like graph functions illustrating relationships and dimensions. They help navigate the zeta complexities of our world. What's your favorite type of map? Genius.
So what did Anders say? Do you mean express T with respect to different bases? Yeah, maybe that's a better way of saying this. So, like, can we express T with respect to different bases? Maybe that's a better way of asking that question. So can we express T using different ordered bases? And if so, like, what does that look like, right? Like, how do we make that happen? But yeah, that's effectively what we want to kind of ask ourselves. And that's what the question I want to answer first. So I need to be a little careful here. I wrote a diagram out, and I want to make sure that I can understand how to make this work. So let's see. So let's consider some coordinate vectors over here on the left-hand side. So if I have two bases, let's say that b and b prime are bases for v, then I can certainly express any vector in v in two different ways, right? I have a coordinate vector with respect to the first ordered basis, and I have a coordinate vector with respect to the second ordered basis. And we know how to transition between these two things. That's exactly the change of basis matrix P. Yep, here comes the diagram, exactly. And then, so we have this kind of similar thing over here, right? So same idea. We have a kind of a generalized coordinate vectors here with respect to b and b prime. And again, we know exactly how to convert between these things. It's exactly this change of basis matrix P. Now, what we're curious about is how to fill in these other gaps. And we've kind of seen how to do this in the last chapter. So there's actually a matrix action that will connect VB to VB. That's exactly this matrix. And then similarly, I can find a matrix for T with respect to basis B prime. And again, I have this way to connect these coordinate vectors using this kind of left-sided multiplication action. So basically, kind of looking at this commutative diagram, we can kind of see that there should be a relation between expressing T with respect to, say, like the standard basis B, for example, and representing T with respect to a different basis B prime. I just have to be able to navigate this diagram in a specific way. So that's what this next theorem is going to do. It's going to help us kind of navigate how we want to construct these two things, and it's going to show us this relationship between these two objects. So let T with respect to B be the matrix of our linear operator from V to V. And again, we're assuming a finite dimensional vector space here so that we have kind of a nice n by n matrix representation. And so the matrices that represent T for other ordered bases I'm going to call them B prime, are given by the following. So let me write it down, and then we'll go back to our commutative diagram, and we'll kind of see why that happens to be the case. So I'm going to my claim is that TB should be equal to P TB prime P inverse. Shouldn't we have T for the second? Oh, the T's are missing in my diagram. Can I write them just as W's? I know what you mean, yeah. Yeah, I know what you mean. So I think in my monkey brain I was just like, oh, like I'm just going to land in some V in the vector space. I can represent it with coordinates in the following way. But yeah, these could be different. They could be the same, or they could be different vectors. I don't know, right? And the action of t acting on v is going to tell me what those output vectors look like. But yeah, that should be okay. Yeah, so I'm okay with that. So what we want to do is we want to say that this action here, so this movement in this direction, really should be equal to going p inverse. So we're going to be moving this way, then this way, and then this way. Right, so we're doing p inverse first, then we're connecting v and w with respect to the prime basis, which we know how to do, and then we're going to have p as our change of basis matrix as the last step. So we're not really proving anything here. We're just kind of summarizing all of the work that we've done previously, right? So we've already done all the work to find this change. We know that p exists, right? We know how to find this change of basis matrix. We know how to connect v with respect to b and w with respect to b. We know exactly how to do that. I know how to find that matrix. So there's nothing really to prove here. We're just kind of summarizing exactly all of the work that we've kind of done so far. Okay, so p is going to be a change of basis matrix. So p is our change of basis matrix. From b prime to b. And I just want to make sure that that's correct. Yeah, it should be from b prime to b is the way that we, I tried to follow kind of what Artin did in the book. So that should be exactly the theorem that we're looking for. So this is interesting. This tells me that all of these matrices that can represent t, just with respect to different bases, they're all similar to each other. If you know what it means for matrices to be similar, it means they share similar determinants. They share similar traces, I think, as well, right? So like there's some nice properties that we get just from the fact that these matrix representations are similar to each other. So that's kind of cool. So that answers the first question. To me, that's all I really need to do. So that answers our first question. How do these matrix representations look? Well, to get from one to the other, I just need to find the change of basis matrix from the two bases that we're working with, and then do some kind of matrix multiplication. So to answer the second question, we're going to go off on a bit of a wild ride. So we're going to start with a definition. That definition is, let W be a subspace. I always want to write soup of a finite dimensional vector space V if T of W is contained in W as sets, then we say that W is T-invariant. Right, so here we're kind of thinking about, so this T is our linear operator, right? So we have this linear operator that's working on V, it's mapping V to itself, and if I can find a subset of vectors that kind of get mapped into themselves, we're just going to say they're T-invariant. And so the question is, like, how can I find these subspaces? What do these subspaces look like, and what kind of properties do they have? So how can we find such subspaces? So what we could do, I guess, is we could start by just analyzing what happens with a single vector. So is it possible for us to think about a single vector as kind of like a basis vector for a subspace, and we'll map it through T, and we'll see where it goes. We'll try to force a particular property on it, and see if we can get something as output. Kernels are T-invits true. Yes, so kernels and the range too, right? The range of our linear transformation should also be T-invariant. And I will leave that for the reader to prove a little bit later. Actually, we can probably just write that down now if you want. Yeah, so we can summarize that as a theorem. So 1, the kernel of T is T-invariant. And 2, the image of T is also T-invariant. And I'll leave that for you as an exercise to try. But yeah, you're right. So these two spaces are two examples of such subspaces. But I want to ask kind of a more general question. So yeah, we can certainly find a couple. So we know that these things exist. Certainly certainly V itself is a T-invariant subspace as well, right? Like if I take all of the vectors in vector space V and I map it through T, it's going to land, it's going to be contained inside of the original vector space. So there are some samples, right? So we know these things exist. I'm not just making up this definition for funsies. But what we want to do is we kind of want to think about like what happens with a single vector. Hi, Plaisant. Feels like we're looking for a kind of cyclic set of vectors. Yeah, I guess in some sense, right? Like in some sense, if we know that it's T-invariant, it should always be contained in W. So at worst, it's only getting smaller, right? As we iterate through T at worst. But at best, it could just be staying stable as well. I think we're going to go with an assumption here that are they going to be, I think that these T-invariant subspaces will be subspaces, although I don't think that's something that we can prove, at least that I'm not going to be thinking too much about right now. But will they be proper subspaces? Probably. I'm pretty sure that the T-invariant subspaces are subspaces in and of themselves, and we could probably prove it. Yeah. Yeah, that's what you're thinking? Yeah, exactly. So this brings up this idea of like nilpotency, for example, right? Like how many iterations do I have to go through to kill something, right? But yeah, so that's kind of like that. And there's a lot of different branches we can travel down just by thinking about T-invariant subspaces. And that's a really interesting story, I think. And we're only going to see part of it. So what happens with a single vector? So what we should probably do is we should probably start by thinking about all of the vectors that get mapped to some multiple of themselves. Because if I think about a single vector and I think about all of the scalar multiples of that vector, that forms a subspace of the linear of V, right? Like if I take any vector and I just think about the spanning set of that vector, that should be a subspace. So maybe I can find collections of vectors such that when I send them through T, they land in the spanning set, right, of that vector, right? So that's kind of what I'm thinking about. So this is like, I want to find the vectors. So we're trying to find V such that T of V lands in the spanning set, right? In the span of V, which we know is just all of the linear combinations of V. So this is kind of where we start. We're going to take a look at this equation and we're going to go, oh, okay, well, maybe I can find some vectors that do this, and what kind of properties do these vectors have? Yeah, okay, and maybe that, yeah, Stuki, thank you for the follow-up to that question. Yeah, you're right. The interesting invariant subspaces are exactly the proper, I gotcha, yeah. So we know that the full entire space, and we know that, of course, the zero vector itself should be T-invariant. But yeah, so if T has proper invariant subspaces, those are interesting things to think about. Yeah, I like that. That's why I like having you around, Stuki. You always pull in the good comments when we need them. Not all heroes wear capes, Stuki. So we've done a lot of this grunt work today to be able to rewrite this in terms of matrices, right? So what we're really going to do is we're going to, instead of thinking about T of V, let's actually just think about the matrix representation of T. So we're going to think about this in terms of matrices. So in terms of matrices, well, this T of V is really just left-sided multiplication, right, by some coordinate vector. And, maybe I should write this as, V with respect to some basis, but maybe we'll just convert this, right? So we're going to convert this vector V from vector space V into a coordinate vector. And we're going to be looking for any vectors x that satisfy this particular equation. So these are the things of interest. And we know that this is a realistic thing to do because of all of the legwork we've done in the last couple hours. So what we want to do here is maybe let's kind of move some stuff around. So maybe ax minus cx should be equal to the 0 vector, right? So we can maybe rewrite this as a homogeneous linear system. And of course we can maybe factor out x on the right-hand side, and we get something that looks like this. So just looking at this, and based on the conversation that we've had in the chat, yeah, we know that x equals 0 is going to satisfy this, right? We know that that's going to be one of those subspaces that's invariant. So that's maybe not an exciting thing to think about. So certainly if x is equal to the 0 vector, this is true. But we don't care about that. We're after the good stuff. We want the good stuff. So here's where things get a little tricky. We're going to say, okay, well, this is a homogeneous linear system. When does a homogeneous linear system have non-trivial solutions? It's going to have non-trivial solutions whenever the determinant of that coefficient matrix is identically equal to 0. So this is homogeneous linear system. So if the determinant of a minus ci is equal to 0, then we have the non-trivial solutions. So that's a big kind of key step here, right? When we're thinking about eigenvalues and eigenvectors, which is where the conversation kind of naturally lends itself to. So I'm just going to go ahead and summarize a couple of the key idea here. So 1, a value C in the field that we're working with, satisfying the determinant of a minus ci is equal to 0, gives a non-trivial solution. To the original problem that we're looking at, which is ax is equal to cx. And these values are called eigenvalues. And the second thing that we can tease apart from this is that for a fixed eigenvalue, any vectors that yield a solution, so the solution set of vectors satisfying a minus ci x is equal to 0. So any of these kind of non-zero vectors that satisfy this for a fixed eigenvalue are going to be in the null space. Why is that important? Because we know they're going to form a subspace. We know the null space should be a subspace. Okay, so that's a key thing to notice here. So now we're going to have a null space of a particular matrix. We know that these are going to be kind of naturally closed under the operations in question here. So we might be able to glean some subspaces out of this problem that might be T-invariant. And we should be able to find a basis for this set of vectors. So that's also kind of important. Okay, so any x that satisfies that original problem of ax equals cx is called an eigenvector that corresponds with a particular c. Okay, so all of these, this collection of vectors for a fixed eigenvalue is called an eigenvector corresponding to c. I don't like putting that here. It's these vectors here, right? So these vectors are the eigenvectors. Corresponding to C. And because they're a subspace, I should be able to pick out a couple of those vectors, form a basis, and maybe this basis is going to be something interesting for us to look at, is kind of the end goal here. Okay, so I don't know how much of this I want to do. Yes. Hi, Sensation. What can I do for you? Never letting that go? Okay. Then I'm never going to give you up. I'll never run around or desert you, Sensation. Okay, let's get this filter off here. I'm just going to do some quick calculations with a 3x3 so that we can find some eigenvalues and eigenvectors, just in case there are some people that are inside the reading group that need this as a little bit of a refresher. So for example, let's let A be equal to 0, 0, minus 2, 1, 2, 1, and 1, 0, and 3. So we can form A minus Ci by just doing a subtraction along the main diagonal. And then we can go ahead and calculate the determinant. So the determinant of A minus Ci, we kind of want to look at when this is equal to 0. So I'm going to skip a little bit of the proof here, but we do get something that looks like this. So I get that C minus 2, C minus 2, and C minus 1 is equal to 0. So this here is called the characteristic polynomial. I just happen to have it in factored form. And then this whole equation is called the characteristic equation. But the idea is, like, if I can factor the characteristic polynomial over the field that I'm working in and find those factors, then those specific factors should be the eigenvalues that we're looking for. So we have C is equal to 1 and C is equal to 2. These are our eigenvalues for matrix A. And then the process is really just taking those values for C, plugging them back into the A minus Ci, and kind of expanding this to homogeneous linear system. So what I'll do is I'll solve one of these so you can kind of see my thought process. So for C is equal to 1, for example, what we're going to do is we're going to look at A minus 1 times I, and we're going to look at this particular matrix, which should come out looking like this, and 1, 0, 2. So I'm just kind of scrolling back here. Anywhere that I see C on the main diagonal, I'm just going to input the number 1, and then just simplify that matrix. And I get something that looks like this. And remember what we want is we want the reduced row echelon form. So we can go through a little bit of work to get the reduced row echelon form. I'm not going to show you that work. Since I feel like most of those who are in the art and reading group have probably taken an introductory linear algebra course, so you've probably done a little bit of this work already. And then what we want to do is we want to look at what this reduced row echelon form is giving to us. So in this particular case, what do we get? We can kind of glean that if we label this as maybe x, y, and z, our 3 variables, then we get that x plus 2z is 0, and we get that y minus z is 0. So there's a relationship here that says x should be equivalent to negative 2z, and y should be equivalent to z. So when I go to construct my eigenvectors, which should come in R3 in this particular case, I know that x needs to be negative 2z, I know that y needs to be z, and I know that z here is the free parameter. It does not have a leading one in the reduced row echelon form. So all of my eigenvectors are going to look something like this. So if I factor out that kind of z component, I get negative 2, 1, and 1 times some kind of free variable. I'm allowed to kind of pick z here to be whatever it wants. So it's this negative 2, 1, and 1 that's of interest to us. This is exactly the basis vector for this particular, we call it an eigenspace. And it's a basis because there's only one vector, so it's linearly independent, and you can see that it spans the space, right? So all of the eigenvectors have the form negative 2z, z, z, and I can take this basis vector and I can multiply it by z, right? Some kind of scalar number, and I can recapture all of the information that I need. So it's a linearly independent spanning set, so it's got to be a basis for the eigenvectors. Of this particular form. Now, I mean, theoretically, we can argue a little bit here that maybe z shouldn't be 0 because we don't want this to be identically equal to 0, because otherwise, you know, maybe we don't care about that because it's not interesting. But I mean, the idea here is that this is a subspace, right, of R3, and I know that the 0 vector has to be a part of that subspace. So whether or not we choose to include z is equal to 0 or not, I still need to include the 0 vector as part of that span, right? I still need that to be a spanning set and to be a nice subspace of the space that I'm working with. So I'm just going to kind of intuitively argue here that z equals 0 is okay in this particular case when we're thinking about the subspace as a whole. Now, something interesting happens when we go to look at C is equal to 2. And I'm not going to go through the full process here, but we do get an RREF here that looks something like this. So we're just going to skip right to the RREF, which is this. And so in this particular case, this implies that x plus z is equal to 0, or the only relationship that we have is that x needs to be equal to negative z. So when I go to construct my eigenvectors, I get something that looks like this. X has to be minus z. I have no relationship for y. Y is a free variable. And I also have z as a free variable. So this is now what my eigenvectors look like for c is equal to 2. Which is kind of interesting. Yeah, so fem exactly, yeah. So this past one is a one-dimensional, one-dimensional eigenspace. Yeah, left as an exercise for the reader, exactly. So in this particular case, we can use properties in R3 to bust this down a little bit, and we could say something like this. We could say, okay, well, let's take a look at all of the stuff that has a z in it, and let's add to that all of the stuff that has a y in it. All right, so we should be able to do this. And we should be able to kind of factor out that z to get minus 1, 0, 1. And we should be able to factor out this y to get 0, 1, 0. So in some sense, this is an interesting example because now we have a subspace that's more than one-dimensional. This one's actually two-dimensional. And we can see that these two basis vectors that we're going to grab are linearly independent, right? So these two vectors, I can quickly see they're not scalar multiples of each other, so they happen to be linearly independent. They span my space. So these are the exact candidates that I need for a basis for this particular space. Okay, so we can grab these vectors. These are going to form our basis. For the space that looks like this, negative z, y, and z. So there you go. That gives you kind of a more numerical example, something we can kind of grasp and hold on to, showing you how we find these subspaces and how we look at trying to find these basis vectors. Hi, Phobos. Welcome back. Now, one question that was really bothering me when I was kind of going back through, looking at my notes, was the following. I was like, okay, can I just union all of these subspaces together in some sense? Like, if I grab all of these basis vectors, I should say, can I just smack them all together into a bigger set? And do all of these basis vectors have this nice property of linear independence? So that was the big question that I wanted to ask myself. So here's my proposition. My proposition is that the union of linearly independent basis vectors corresponding to our distinct eigenvalues they remain linearly independent. So that's kind of interesting. That's interesting. Now, there's a couple things that we are going to need here. We do need distinct eigenvalues. So when I was looking through a lot of these proofs, I think the idea was, I have an eigenvalue, a single eigenvector probably pops out of dimension 1, and then it's really easy to kind of see that all of these things, when we union them together, becomes linearly independent. So there's a little bit of trickery that probably happens here when we don't quite have enough, or we have in this particular example, we had a repeated eigenvalue. So there's maybe a little bit more that I have to think about, but this is what I was able to kind of come down to with the short amount of time that I had to look over some stuff. But this to me feels important, right? So let's get some assumptions rolling here. So let V1, V2, up to Vk be our eigenvectors with corresponding eigenvalues, and we're going to call those the corresponding distinct eigenvalues, let's say. So we don't want to get a 0 here. Okay, so we're just going to label, maybe let's label this up to CK. Okay, so I have a specific eigenvector that maybe is corresponding with a specific distinct eigenvalue. So in some sense, if I'm given these kind of k distinct eigenvalues, and I can grab at least one vector that corresponds with these distinct eigenvalues, then these should all be linearly independent, is what we're going to be trying to prove. So let's go ahead, let's consider v1 plus v2 all the way up to vk is equal to the 0 vector. And we're going to proceed by induction on k. So when let's see, when k is equal to 1, I have a single vector. And so this is, we have that v1 is equal to 0, and so our base case is true. So now what we want to do is we want to start with our induction on k and see what happens as we start adding more and more of these particular vectors. Okay, so now when k is bigger than 1, there's a couple things that happen. What am I writing down here? Yes, that seems to be true. And we can left multiply here. That leads to that. And then we do a subtraction. Okay. Okay, I saw something pop up in the chat, so give me a hot second to write something down. You need to consider a linear combination, not a sum. How does this work? That's what we're going to be doing here. We're going to be looking at the linear combinations, right? So, okay, give me a hot second here to think about this. So, I think that the sum of the vectors here, I think it's an equivalent condition, isn't it? Or if all of these are identically equal to 0, this would force all of our vectors to be equal to 0, right? So it's an equivalent condition to looking at a linear combination, if I remember correctly. Isn't it like if this implies that every single vector is 0? I think this is what we're working with. We're working with like if the sum of all of our vectors is 0 implies the only solution is that each vi is equal to 0. Then they're independent, right? So it's a bit of a weird way. I agree with you. I wouldn't normally think through a proof this way. No, it's a little different. I think I'm trying to, so I think from what I was reading, they're trying to use this, right? And it should be equivalent to linear independence using scalars, but instead of using scalars, we're going to look at the sum of the vectors and what we need to do is we need to force all of these vectors to be the 0 vector. So if I could show that the only solution is the 0 vector, then I know that these things are independent. That all of these vectors are forced to be the 0 vector. So it's equivalent, from my perspective, it feels equivalent to if I have a sum of ki vi equal to 0, this implies all of the ki's are equal to 0. It feels equivalent to me. But I'm happy to be corrected if I'm wrong. So it feels like in one sense you're forcing all of the vi's to be fixed, and then you're looking at the scalar multiples and you're saying, okay, well, if all the scalar multiples are 0, then this is the result. And in the other way, you're saying, let's just fix all of the ki's to be 1. Right? And if the only solution to this problem is that each one of these vectors is the 0 vector, then they have to be independent. Seems to be true for eigenvectors. Wasn't this in Artin? I could be wrong, but I feel like this was in Artin somewhere. It's worthwhile for us to figure this out, because it's going to be it's the only way that I know realistically how to prove this thing. Vector spaces, basis and dimension. I think he talked about it in like the independence section. So real vector spaces. Abstract fields, basis and dimension. Maybe it was inside here. Linear relation. Yeah, so that's one way that we usually think about independence. Darn, I wish I would have written down a little bit more, because I read this and I was like, oh, that's exactly the thing that I need. Yeah, that I remember all of that stuff. That's the dimension. Darn, okay, I thought I saw it in Artin somewhere. Maybe I'm just going crazy. Is this in the direct sum section? Here it is. Oh, it's in the direct sum section. Yeah. Here it is. It's right here. So maybe it needs a little bit more legwork for me to be able to verify. But yeah, so the set of all such vectors is called the sum of the subspaces of their span. So we create a vector that is an addition of all of these vectors. And then so the subspaces are called independent if no sum with the is 0. Right, okay, so I need to use this, right? So I'm using a little bit more extra firepower, I guess. Right, so we're checking to see if all of these subspaces are independent of each other. So maybe I need to, let's port this over. So it's called the sum, so we're using this here, right? So, dependent. Right, so we're using this from Artin. So it's a little bit different from what my intuition had said. But we know that these are all subspaces, so we should be able to utilize this particular idea in Artin to get the job done. Okay, so my apologies there for being a little bit off, but we're using this idea here. Okay, so if I can show that this equation implies that all of these vectors are 0, then the subspaces themselves are independent, right? Which means they should have independent basis vectors. Yeah, so maybe it's true. I think you're right. It's not true in the general case, but in this particular case, I know that each one of these vectors that we're taking is a vector from a subspace, and that's, I think, the important part here. Yeah, it's a vector from a subspace, so that when I add these up and equate it to 0, I can get independence of these subspaces by looking at this particular equation. Let me know if that makes sense, or if we need to chat a little bit more around that. I'm happy to chat a little bit more around that if we need to. So I'll put a little star here. What page is that? So if you want to read that in Arten, it's page 102. And so you are right that it shouldn't work in the general case, but it should work for the eigenvectors that we're working with, because each one of them individually forms a subspace. Yeah. Yeah, so this is definitely a direct sum path, and my apologies for not being immediately clear that that is the case. Okay, so what I did after I kind of found this was to think about that sum. We're going to scalar multiply it by C1, and that's going to give us something that looks like this, which should be equal to our 0 vector in V. And then the next thing that we can do is we can left side multiply equation 1 by some matrix A. So let's go ahead and left multiply. And if we go ahead and multiply through, we're just going to get like AV1. We know what that looks like. We know what AV2 looks like, and so on up to AVK. Of course, this remains the 0 vector over here. And then each of these AVIs gets mapped to C times that particular thing by the action of A on that particular eigenvector. So we get C1V1 plus C2V2 and so on, up to CKVK. So now we have a couple other things that we have to work with at our disposal. Ander says, maybe it's worth mentioning here that we're taking the image of T as the direct sum, not necessarily all of V. Yeah, because we're doing the, yeah, exactly. Because we're doing the left-sided multiplication by A, all of these vectors that we're really working with are inside of V. I agree with you, yeah. At least all of these scalar multiplied vectors too, right? So you're saying that these as well, yeah, okay, so these V's as well should be inside of vector space W, which is the image space. Yeah, I gotcha. Yeah, I'm okay with that. All right, so let's go ahead and subtract 1 and 2 from each other. And we get the following. So we should get C1V1 minus C1V1, so that's just 0. And then we will get C1V2 minus C2V2, so we get C1 minus C2 V2, and so on until we get to C1 minus CK VK. And then, of course, the subtraction of the 0 vectors here should give us the 0 vector as well. And now we are just going to use this idea that all of these C's have to be distinct. So none of these are equal to 0. So that's really going to force one particular solution, and that's that all of our v's here are going to be identically equal to 0. Okay, so an induction on K should get the job done here. That's not saying if it's invertible. Diagonalizable doesn't imply. Yeah, we need to also. You need to have non-zero eigenvalues too, right? For invertibility. All right. So if I have all of these distinct eigenvalues and I can grab an eigenvector that corresponds with each one of those distinct eigenvalues, then I know that that collection of vectors should be linearly independent, right? And all of these kind of subspaces are independent of each other in a very, very kind of nice, organized way. And as a corollary, basically, we're going to say that we can form a basis, basically, for Fn if I know that I have n distinct eigenvalues. So that's really nice. So in the nicest sense, if I take my matrix that represents the linear transformation and I can find n distinct eigenvalues, I know that I have an easy way to move forward. I know that we have a basis for Fn, and we're going to be able to show that our matrix is diagonalizable. Yeah. Yeah, exactly. So Ultimate is asking a good follow-up question. Does that mean our matrix has full rank? And the answer, I believe, is going to be yes in that case. Well, I have to be a little careful here. Not necessarily Ultimate. I think if we have an eigenvalue of 0, we run into a problem. So I think it's less about A having full rank and more about 0 not being an eigenvalue. Because if we go to diagonalize and we have 0 along the main diagonal, we know the determinant is 0 for that matrix. So we have a singular matrix. And I think we're going to run into problems with the rank, right, in the reducer echelon form. So hopefully that clears it. So maybe not. Yeah, maybe not. Now, what we do get, though, is if 0 happens to be an eigenvalue, I know that then I can find a non-zero eigenvector that forms a basis for that subspace. So even though the matrix could be singular, I still should be able to get a corresponding eigenvector that's going to help me get a basis for Fn. So there is a little bit of a non-intuitive gap here, I think, right? Like the eigenvalue of 0 does form a bit of a problem, but I still should be able to find a non-zero vector that I can use as a basis if c is equal to 0 in this case. Is an eigenvalue of 0 a sane thing? Yeah, it means that a whole group of vectors gets flattened. So but you're going to lose dimension. You're going to lose dimensionality if you get c is equal to 0 as an eigenvalue. All right, so this leads us to what I would consider the important part of the discussion. We have n linearly independent vectors, and we can arrange them into some kind of matrix. And this allows us to create an interesting change of basis matrix. So we can basically arrange all of these vectors as columns. And now we have this interesting change of basis matrix that's going to allow us to do a little bit of work with regards to the representation for our linear transformation. So these are our linearly independent vectors. And we can think about this as a change of basis. Right, we're changing into what we call, like, what I would call an eigenbasis, rather than maybe a standard basis that I might pick. So in some sense, this collection of eigenvectors is an interesting basis to pick, and it has some really nice properties. So let me just kind of jot some of that down. So we recognize I'm going to recognize this as a change of basis matrix. Right? These are linearly independent, so it should have an inverse. And P has always taken us from B prime to B. So B prime in this case is the what we call the eigenbasis. And kind of in the background, the tools that we were using are like everything's been done in the standard basis with our analysis. So this matrix P should convert us from the eigenbasis that we have back to our standard basis. And then we're just going to go ahead and we're going to multiply A by P. So if we go ahead and left side multiply by A, we should end up getting something that looks like this as our columns. Now this left-sided multiplication is going to convert all of our columns into things like C1, V1, right? So the we have this equivalent expression here due to that relationship that we have with A, C,
Following
and V,
the conventions of notation in Artins, is P always with respect to the canonical basis of Fn?
Following the conventions of is Artins P always with respect to the canonical basis. So P is always a change of basis from the, I think he's usually going from like a non-standard basis to the standard basis typically, is how I think about P. Although the inverse does the opposite. So it's, you know, you can theoretically create a change of basis in any direction that you want by either observing P or P inverse. But yeah, I assume that Artin's always doing everything with regards to the standard basis as kind of the place we're going to. At least that, from my perspective, that makes a lot of the computations easier to work with. Okay, so Ci here are eigenvalues. And the interesting part now becomes our ability to rewrite this in terms of a diagonal matrix representation. So what we can actually do now is we can think about this as a matrix that consists of our eigenvectors as columns. And what we get on the right-hand side is a multiplication by what we call a diagonal matrix. Okay, so this is a diagonal matrix. All of the other entries off the main diagonal are 0. Okay, so A times P. So basically what we have is we have A times P is equal to P times D, right? Where D is some diagonal matrix. Yeah, Placente's right. As soon as you have a 0 eigenvalue, then you're into a non-zero kernel, exactly. And that's always the case that we have to be a little careful about. But just because we have a 0 eigenvalue doesn't mean that we cannot form this matrix P, right? It still should have an associated eigenvector that's not 0. And this should still be this should still be linearly independent, right? So this change of basis, it should still work, despite the fact that we have a singular matrix representation for our linear transformation. All right, so we have kind of the following, and of course we can rearrange this to get a diagonal matrix in terms of matrix A. So that's going to be the theorem that we pop out here after doing a little bit of legwork here with regards to our eigenspaces. So this is the big one. That is if an n by n matrix has n distinct eigenvalues, then we know that we have the following relationship where D is equal to P inverse AP, or vice versa. We could write it as PD, P inverse is equal to A. So this is going to be a diagonal matrix, and the eigenvalues, so this is going to be consisting of the eigenvalues on the main diagonal. And we know exactly what P looks like. P is the columns, and each of the columns in P is going to be the eigenvectors that we found from all of those particular eigenspaces. So P consists of the corresponding eigenvectors and I mean specifically we're kind of taking the basis vectors. And we want to take those eigenvectors as columns. Yeah, Reese is here. He's about ready for dinner, so we got to wrap this up pretty soon, my friends. But I got just like a couple more interesting things to potentially chat about. We talked about the other T-invariant subspaces. The last thing I really want to show you is that with regards to the eigenspaces that we're working with, the eigenspaces are all T-invariant. Oh god. That's a good clip, Anders. That's a good clip to get for sure. So, like I said, this is the kind of the last little bit that I want to give to you for today, and that is if. Hi, Andy. Welcome in. He was just out.
Hello there.
General Kenobi!
I'm so happy that you clipped that. Yeah, Reese definitely wants some food, so we will we'll tend to Reese. We'll get him out for a walk. But I want to leave you with this, and this is kind of the start, I think, of where the conversation goes, right? So we have these eigenspaces. We have these kind of basis vectors that we can work with. It turns out that these eigenspaces are T-invariant subspaces of our map. Hyped to learn about T-invariant subspaces. Yeah, I would love to learn a bit more.
One slap, you're gonna love my nuts. Two slaps, you're gonna love my nuts.
It's nuts on there. That's so nuts.
You're gonna love my nuts. Hate my nuts. Watch my nuts. Slap my nuts. I love my nuts. Gonna make America love my nuts. One slap at a time.
Lucas, if you posted your question on Discord, I'll take a look at it. But I want to kind of cut this off so I can port this over to YouTube for the simple group in case I want to take a look at the speed run of linear algebra. But yeah, if you posted it up on Discord, I'll take a look at it and I'll respond back to you here over my next cocktail. And yeah, if anyone has a good source for T-invariant subspaces of a vector space, I would love to get that source. I should check to see if Friedberg has anything on these T-invariant subspaces, but I would also be curious to know more, because my major question is, how hard is it for us to prove that any T-invariant subspace is a direct sum or direct product in some sense, right? An external direct product of eigenspaces. To me, that's the interesting conclusion to that story, and I don't know how to connect those two gaps yet. So that's where I want to learn a bit more, personally. Is anyone online right now? Thank you very much, Fem. I'm glad you had a good evening. Is anyone online that we can raid right now? Is it a prime decomposition theorem? Ooh, I don't know.
Said it right. Prime decomposition theorem states every integer has a unique prime factorization. What zeta math concept will we tackle next?
Good cocktails, yes. And Anders and Plaisant, I will... no, not that. Wrong one, show. Wrong one. I will drop off a couple QED points for you guys.
Problem solved.
Ooh, ultimate. Yeah, we can take a look at that. And then we want to get Plaisant in here as well as a thank you.
QED.
For reminding me...
GPT%.
I wanted to thank you for reminding me that we had to use a little bit of that backbone and Arton to get the job done for the linear independence. So Cat Vinel, a vanilla cat. That's not correct. That is not correct. Oh my god. Andy, I have a funny story for you if you're still here. Invalid username. Oh, maybe I don't have to put the at. Cool, let's go raid Kate and say hello. Hopefully they're doing maths or some kind of science. And hopefully they're not hot tub streaming. Hopefully Ultimate Doom has not made us go into a hot tub stream tonight. Alright, bye guys. I will see you probably at some point tomorrow. Abstract Algebra is going to be canceled for the night because Dave and I are going out to have some cocktails. And maybe I'll see you tomorrow night.
But you'll thank me
for some
when you
abstract
realize
algebra.
how much brilliance
Until
I bring
then,
to the
take care,
table.
folks.
A genius like me is rare. Grasp it while you can.
We'll talk to you guys later. Bye.